So it's my pleasure to introduce tonight's guest speaker, Professor Christine Done. Christine completed her PhD at Cambridge on X-rays from black holes. Following this, she went on to NASA/the Goddard Space Center on an NRC fellowship, which we've explained what that means before, for the next 2 years, where a highlight was being part of ground control flying an X-ray telescope in the payload bay of the space shuttle. After NASA, Christine returned to the UK on a junior 2-year and then senior 5-year research fellowship from the UK Research Council before getting a tenure at the University of Durham in 2000. Christine was promoted to full professor in 2006, becoming one of the first women to hold this post. She is also a stipendary visiting professor at the Kavli Institute for Physics and Mathematics at the University of Tokyo. After having spent the academic year 2016 and 2017 in Tokyo on a sabbatical working with the Japanese Space Agency. Christine is one of only 2 European scientists supported by the European Space Agency to be part of X-ray, the next Japanese/US X-ray telescope, also chairing one of the science working groups for this mission, as well as being a member of the Science Management Office, whilst also chairing one of the science working groups for the Atlanta X-ray satellite, due for launch by ESA in sometime in 2030, hopefully if they keep that schedule. To date, Chris has contributed to 545 papers and has 25,985 citations, with the latest contribution being systematic collapse of the accretion disk across supermassive black hole population. So again, it's been my pleasure to introduce Chris. Can we please provide her a very warm expert in Sweden astronomical welcome?
So thank you very much for that introduction. I was just getting my PowerPoint on share, and let's hit slideshow. Okay. So today, what I'd like to talk about is my kind of specialist topic. I do get paid to think about and do research on black holes. It's an awesome job. And I do also get paid to work with every major space agency on the planet, which again makes the job even more awesome. I also get to introduce myself at parties as a rocket scientist. You heard in some of my biography there, all the space agencies that I've worked with. And that does get a good reaction at parties. It has to be one of the best ways of introducing yourself. But many of you will be sitting there thinking, hang on, black holes? She's talking about black holes. Well, where does rocket science come into black holes? Because the thing about a black hole, its main distinguishing feature is it's black. And the thing about space, your basic space color is black. So how are you supposed to see them? And so this is what I'm going to talk about today. I'm going to describe what black holes are, and I'm going to describe some of these recent breakthrough results that have enabled us to see them. And I'm going to describe how it connects to rocket science. And then I'm going to talk about some of those. Well, if black holes really exist, then what about all of those crazy science fiction plots? Can you use them for space travel, time travel, alternate universes, all of the fun stuff. So that's where we're going in the next 45 minutes. So let's make a start with what is a black hole. And black holes are all about gravity. And you've probably done something about gravity when you were at school. And you know there's something called an escape velocity. If I stand here and I throw something up, so imagine me throwing something up because the screen isn't really big enough to show this. If I throw something up, it will go up some way and then come back down again. If I can throw it faster, it will get higher before gravity pulls it back down. And the whole idea is that if I threw it fast enough, I'd be able to make it go so high that actually gravity never turns it around and comes back. So this is the idea of an escape velocity. It's how fast I'd have to throw something on the surface of something like the Earth for it to actually escape from the Earth's gravity. And then you can start to think, hang on, light has got a speed. It's the fastest thing that there is. So if I made gravity so strong that the escape velocity was the speed of light, then not even light would be able to escape from the surface, and it would be always dark. It would be black. It would be a black hole. But even when they were speculating about this 200 or 300 years ago, they realized then with Newton's gravity that gravity seemed to only affect things that had mass. And they were pretty sure, even a couple of hundred years ago, that light didn't have mass. So then maybe light didn't affect gravity. But Einstein's idea of gravity was completely different to Newton's. So Einstein not only gave us a better set of equations to calculate the effect of gravity, Einstein gave us a way to think about the more basic question, which any 5-year-old would ask at this point, and in fact, they often do. Please, miss, what is gravity? I was doing a talk in a primary school. And another question was, please, miss, if we're made of the same stuff as the animals, why are we different? And so to both of those questions, I was saying, that's a really good question. And we don't really know the answer. Become a scientist, maybe one day you'll find out. So with gravity, our best answer, but we know it's not the ultimate answer, but our best answer is Einstein's gravity. And Einstein said, think of the surface of space and time like the surface of a trampoline. If there's nothing on the trampoline, it's stretched nice and tight. And if I put something very light across the surface of the trampoline, so like a ping pong ball, it's not going to do very much to the trampoline surface. It will just go across in a straight line at a constant speed. But if I put something heavy on the surface of the trampoline, it bends the surface, not just at the point where the mass has been put, but it bends the surface out to larger radii, like this picture here. And then you can kind of see that anything that goes across this curved surface, its path is going to get curved. the problem with the trampoline analogy is that it kind of depends on gravity to work. You need gravity to pull the mass to bend the surface of space-time. And so sometimes this gets a bit confusing. A better way to think about it is to just think about curved surfaces. So I could have like the surface of a tennis ball, or I could have a flat sheet of paper, or I could make more funky shapes. And now I'll take some very, very obedient ants and I'll put ink on their feet, claws, not really sure what ants have, and say to each one of them, go north. So they're just going to walk in a natural way, left foot, right foot, middle foot, left foot, right foot, middle foot. And on the flat surface, if I set them off going in the same direction, they'll keep going in the same direction at a constant speed because they're walking in a natural way on a surface that's flat. But if I do this on a surface that's curved, if, say, I set them out from the equator of a sphere, they're a little bit apart on the equator, and now they're walking in a natural way north, due north. And the one on the left is thinking, you know, I'm sure the one next to me is getting closer. And the one on the other side is thinking, it's really odd. We started off that far apart, but now we're this far apart. Maybe there's some action at a distance force dragging us inexorably together. Shall we call it gravity? And the other one's going, no, I think we'll just say we're walking in a natural straight line path on a surface that's curved. Why don't we just call it curved space-time? And so this is the whole idea of Einstein's gravity. It's not some spooky action at a distance force like it is in Newton's gravity. The sun is here, the earth is here. Look, no hands. No. The sun is here. Oh, I've lost my cursor. The sun is here. It's curving space-time out at larger distances. The earth is over here, and it's responding to the curvature under its feet. And that's all there is to it, according to Einstein. Let me see if I can get a laser pointer, because that would be better. So that's the really big idea of Einstein's gravity, that we can't, it's not just that we can calculate the effect of gravity, we can have a kind of picture of what gravity actually is. So I've been showing it you as this kind of two-dimensional surface of space-time with a mass on top of it. But again, you're thinking, but space is three-dimensional, so how does that work? Well, it's difficult to draw, but it kind of goes like this. So you can think of the mass warping space in a whole three-dimensional way around it. But it's also warping time as well, and we're certainly not going to draw that. So let's go back to our two dimensions, and from now on, I'm going to draw the curvature of space-time, kind of like a flat sheet with a dent in it. And so this new idea of gravity gives you actually something new instantly. Newton's gravity affects things with mass, so maybe it doesn't affect light. But Einstein's gravity isn't like that at all. Anything that goes across the curved surface of space-time, its path is going to be curved. Light goes across the curved surface of space-time, so it's going to be affected. Its path is going to be affected by the curvature under its feet. And so this gave them, at the beginning of the 20th century, it gave them a kind of way of testing this new idea, this funky new gravity. Eddington realized that if he was looking at a distant star that happened to be along a line of sight that from the Earth passed close to the sun, then its light would go through those highly curved bits of space-time close to the sun. And so its path would be curved. And so we'd see a shift in its position. And so this gave a way of actually observationally testing, did this happen or not? Now, the problem is any star which is projected close to the sun, it's close to the sun, and the sun is much brighter. So it's really hard to see, but you could wait until the moon comes in front and eclipses the sun, and then you get both a solar eclipse and you get to make this experiment. And so that's what they did. And this is basically what they saw in terms of the shifting positions of the stars. So they measured the positions of the stars during a solar eclipse. And then 6 months later, they measured the positions of the stars where the sun's the other side of the sky, and the positions had shifted by exactly the amount that Einstein had predicted. So this was like amazing and clear evidence that gravity affects light. In which case, we're back to our idea of black holes. If gravity affects light, then if we could make gravity strong enough, if we could make a surface that had gravity so strong that the escape velocity from it was more than the speed of light, light couldn't escape from it, it would be forever dark. It would be a black hole. So let's think this one through. How does it work with this new picture of gravity as curved space-time? So here's a cut through of the Earth orbiting around the sun, not to scale. So the yellow blob is meant to be the surface of the sun. The red is the orbit of the Earth around it. And the white lines are like the grid points showing you the curved space-time. So let's make gravity stronger. Well, the way to make gravity stronger is to put more mass in the same space, or take this mass you've got and crush it smaller. The sun's kind of big and it's a bit hard to add a significant amount of mass, so let's crush it. So let's think about what happens if we were to take the same amount of mass and crush it. So what we do is we make it smaller. So we'd make the gravity at its surface stronger. So we'd need to be going faster in order to escape. So we've now gained access to these areas of space-time before they were inside the sun. But now we've got some much more curved space-time that we can start to think about the effects of. So let's crush it again and get it to the size where we'd have to be going out, directly out at the speed of light in order to escape. So if we now crush it just a tiny bit smaller, it's a black hole. No light can ever escape from it. So what about some of those ideas then? Often we think that black holes are such strong gravity that any planet going around would be inexorably drawn into the black hole. But now you're looking at this picture and you're going, well, that's obviously not true. The Earth is still responding to the curvature of space and time under its feet. So its orbit is where it always was. Nothing at the Earth's orbit in terms of the curvature of space and time has changed. The thing that has changed, of course, is the sunlight has gone, so all the plants will die, so all the animals will die, and we will die. But apart from such minor considerations, the orbit of the Earth isn't inexorably pulled in to the black hole. So that's one sci-fi trope down, but clearly we have made much, much, much stronger gravity down close to this event horizon, the place where you have to be going outwards at the speed of light to escape. But the more fun question is what's underneath? What's in the region below the event horizon? Well, we'd love to know, but since no light ever gets out, we have no way of knowing. We can use the equations to trace back, and they're pretty okay until you get close to the bottom of this black hole, where you get close to the point at which the equations explode. They start predicting an infinitesimal point of infinite density, which is the singularity at the bottom of a black hole. In physics, when we get infinity out of our equations, it normally means we've done something wrong and taken them somewhere they don't want to go. And so probably this thing has some structure, but our equations, our understanding of gravity isn't good enough to predict what happens at those sorts of tiny size scales and intensely strong gravity. And anyway, it's decently hidden below this event horizon, which is like the last place we can get any observational data on them, where we can do any experiments to test our theories. So for most of the rest of the talk, I'm going to be above the event horizon, where we can actually test these new ideas of Einstein's gravity in really, really strong fields. In fact, I've talked about light escaping, but actually a better and more kind of intuitive way, as well as being mathematically correct, is to think of a black hole as kind of like the plug hole in a sink. And space and time are the things that are flowing towards the plug hole. And they're flowing in at a rate that's sort of the free fall rate. So far away, space and time are moving slowly. And then as you get closer and closer to the event horizon, they're accelerating, and the space and time are falling in faster and faster. And at the horizon, they're falling in at the speed of light. And so then you think of escape velocity as kind of like swimming against the current in a river. If a river current is going that way and I'm swimming this way, as long as my swim speed is faster than the current, I'll go forward. Maybe slowly, but I'll go forward. But if my swim speed is not faster than the current, even though I'm swimming forwards, I am going backwards. And that's the way to think about light, trying to get out from under the event horizon. The light is pointing radially outwards, but it's not fast enough to get out. The space and time sweep it down into the singularity of the black hole. So that's how to think about black holes. So what would we need to do to make one, to have one to play with? Well, okay, let's think about making one, maybe not from the sun, let's make one from the Earth. So if I took the Earth and I squashed it and squashed it and squashed it and squashed it into the size scale so that my escape velocity was the speed of light. Not sure how big that is on your screen. It should be about 1 centimeter. You have to take the mass of the entire Earth and squish it into a sphere of size 1 centimeter. That's how strong the gravity is for a black hole. At which point you're going, yeah, I don't think we need to bother about this. This is not going to happen. Correct. It will not happen for the Earth. But actually, it can happen in the lives of the most massive stars. Not stars like our sun. So stars in general are just taking hydrogen as fuel and fusing it together, doing nuclear fusion reactions deep down in the center. And in Einstein's, one of his other amazing breakthroughs was the realization that mass could be a sort of energy. So if you fuse 4 hydrogen nuclei together, make 1 helium nucleus, you put them on a balance, and the mass of the 1 helium you end up with is just slightly lighter than the 4 hydrogen particles you started with. You lost some mass, you gained some energy. And that's how the sun and pretty much all the other stars in the night sky shine. But while stars are big and they have a lot of hydrogen fuel, they are finite. And at some point, they run out of hydrogen. But it's the hydrogen that's doing the nuclear fusion to make the energy that keeps the star hot. And then the pressure of the hot gas pushing out has balanced gravity pulling in. Only then we run out of nuclear fuel to keep the gas hot. What happens next depends on the mass of the star. For stars like our sun, there's some little kind of, they don't have enough gravity to completely crush their cores. But for the most massive stars, that is not the case. For the most massive stars, the biggest, the ones with the most gravity, when they have run through their hydrogen fuel, they lose it. They go through a complicated series of last-ditch attempts to stave off the inevitable, but the inevitable happens. And you get utterly dramatic implosion of the star. The core implodes, the outer layers go, oh, who took the floor away? And then they kind of smack down onto the core, smash it, splat out. They form this supernova explosion. So there's one here. And this is one single dying star. And for a couple of months, its light outshines the entire light of 100,000 million stars, normally shining via these nuclear fusion reactions. For a few months after this explosion, this one dying star can be brighter than an entire galaxy of stars. It's that dramatic an explosion. So that's the end point of the most massive stars. And we know of nothing that can keep that core held up against gravity. It collapses underneath its own event horizon and is gone, gone black. So I hope I've given you a plausible way to think about making a black hole on the black background of space. So how are we going to test this? Well, the key is don't look for a black hole, an isolated black hole on the black background of space. Look for something that's got a bit more light emitting from it. And this is where most massive stars, actually, they hang out with their friends. So a massive star that runs through its nuclear fuel explodes spectacularly, core implodes, becomes a black hole. Well, the star that it was orbiting around it is still orbiting around it. And if they're close enough, the star can be lunch. And so that's what you're seeing in this little animation here. You're seeing the one in the center has collapsed to a black hole, and it's orbiting around this companion star. And that star is close enough that gravity on the front edge of the star actually points towards the black hole rather than towards the center of the star, because they are quite close. And so then the outer layers of the star start spiraling down into this enormous gravitational potential. But then that's another source of energy. On Earth, we get energy out of gravity in things like hydroelectric power. You have water falling under gravity, and the energy turns turbines. Well, here we have the material coming from the companion star, and it's spiraling into this incredibly strong gravitational potential. And that energy is heating the material. So it's not, it heats it not just red hot or even white hot. It heats it to X-ray hot temperatures. And so you have this idea that you can have an X-ray hot disk of material shining really brightly before. This is all above the event horizon. It's kind of like the final scream of this material before it disappears forever from the universe down the black hole. So if we could look at the sky with X-ray eyes, we would see nothing, precisely nothing, because our atmosphere is thick as a brick. And no X-rays get through our atmosphere, which is very good news for our DNA, but not such good news if you want to go look at X-ray bright disks round black holes. And so if you look, what you're seeing here is the transmission through our atmosphere. So when you look in optical light, then obviously optical light from the stars can get through. And then some infrared, but most infrared gets blocked. And then we start to see into space again in the radio part of the spectrum. But anything apart from radio and a bit of infrared and optical, just blocked by our atmosphere. We can see nothing apart from these little wave bands. We can see nothing from the surface of the Earth. If instead we go above our atmosphere, then we could go and look at the sky with X-ray eyes outside of our atmosphere, and we could go and see what's there. And so this was 50 years ago now, when they, at the dawn of the space age, they flew the first X-ray detectors on little rockets. They didn't actually know what they were going to see. At that point, people were thinking of black holes, but they were thinking of isolated black holes on the black background of space, and thinking, well, there is no way to see that. But they thought, well, it might be fun to put an X-ray detector on a rocket, light the blue touch paper, stand very well back, and see what they got. And so that's what they did. And they actually, these very first rocket flights, one of the things that they discovered is now known to be one of these black holes surrounded by this intensely luminous, like glowing X-ray halo saying, look at me, and which is the material just falling towards the event horizon. So he got the Nobel Prize for that, because essentially X-ray astronomy transformed black holes from being some theoretical extrapolation of Einstein's equations into being observable science. And it also means that if you study material falling into black holes, you get to call yourself a rocket scientist, and you get to fly an X-ray telescope in the payload bay of the space shuttle. So I was in ground control, not in the space shuttle, but in ground control, wearing the snazzy headset, controlling an X-ray telescope in the payload bay of the space shuttle. I'm mainly a theoretician, you know, so that was a bit wild. So let's go look at the sky with X-ray eyes. But first, let's kind of ground ourselves by looking at the sky in the optical. And I'm going to show you pictures where in optical light, the plane of our Milky Way galaxy goes across the middle. And you can see there's quite a lot of gas and dust in that plane that absorbs the light from the stars further away. But you can see very clearly the stars in our Milky Way galaxy, and the galaxy is like a circle when you look at it face on, but it's much thinner than it is wide. So when we look through that distribution of stars, it's quite narrow. So the stars are here along the middle of this plot, but especially in the middle, in the central bulge of our galaxy. So now let's switch to an X-ray view. Oh, so the sources picked out in red here, these are mainly the bright sources, and they plainly follow the same distribution as the stars in our galaxy. Well, that makes a lot of sense. If they're dead stars with a stellar companion, they would, of course, be connected to the distribution of stars in our galaxy. So many of these red dots are the sorts of systems we were just talking about, where you've got a black hole and you've got a companion star that's close enough that it's losing its outer layers and they're spiraling down the black hole, and the enormous energy is kind of highlighting the position of that black hole. It's not on the black background of space. It's got this X-ray halo around it. But that's not the only dots on this picture. There are all these blue dots that seem much more evenly distributed across the sky. And these are fainter sources. And they're a bit interesting as well, because what you're looking at there, oh, I have the spinning wheel of death. Oh, hang on. Ah, right, okay, that's because I went too fast. So the sorts of stars that we see in our own galaxy, they can be smaller stars like this. But if it was another high mass star, then at some point, that star itself, that companion star, would run out of fuel and it could collapse to a black hole. And then we'd have two black holes going round each other. Ah, is this ringing any bells?
They are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time.
So if you have a single black hole on the space-time trampoline, fine, it's just a dent. But if I have two black holes orbiting around each other, I've got two dents, and those dents are moving. And if I have dents on a trampoline that are moving, then there's a wave on the surface of the trampoline that reflects that motion. And a wave carries energy with it. And so this orbit of these two black holes around each other, the gravitational wave is carrying energy away, which means that the orbit's shrinking, which means the two black holes are going around each other faster, which means they do more gravitational waves, which means the orbit shrinks further and further and further, and eventually their event horizons should merge in a burst of ripples in the fabric of space and time. And this is what they saw in the gravitational wave detection 5 years ago. And I can't even begin to describe how heroic this measurement is. These waves in the fabric of space and time, they are incredibly small. And yet they were able to convincingly detect them. So what you're seeing here in the red line, this is the data. And you can see there's kind of wavy things here. And this is the two black holes on their kind of like final approach before they merge, their event horizons merge into each other, and then it all kind of settles down. So you're seeing here the merging of two black hole event horizons. And the line underneath is the prediction you get from Einstein's gravity. It's amazing. And in some sense, this is the strongest field we could ever hope to measure. When we were looking at that X-ray hot gas, we were close to the event horizon, but not exactly at it. This is exactly the event horizons merging. And Einstein's gravity gives us a prediction as to what this gravitational wave signal should look like. And it looks like their data. It is incredible that they could see this. Right, now we'll go back to those other X-ray sources, those fainter X-ray sources scattered around the sky, because there's another of the really recent breakthroughs that's connected to those. So what those fainter sources distributed evenly across the sky are, they turned out to be X-ray hot disks, yes, but not around stellar mass black holes. They're around supermassive black holes in the centers of other galaxies. So the idea goes something like, well, in the center of a galaxy, maybe you have a lot of stars, especially when galaxies are growing and forming. Maybe you have a lot of stars in a star cluster. Maybe many of them become black holes. Maybe those black holes merge. Maybe then you have gas flows into the center of a galaxy. So you're building up this central black hole by the mass that it's secreting through this disk. And galaxies merge sometimes, so there'd be more mass growing the black hole. Maybe there are two black holes, one in each galaxy, maybe that would merge. So you could have this complicated history of the growth of the black hole in the center of a galaxy, and the galaxy's evolution as well. So how could we go see those if they weren't currently having this X-ray hot disk? Because actually, most black holes in the centers of galaxies aren't growing very fast. They don't have large amounts of material falling onto them in the present universe. So aren't we back to looking at the black hole on the black background of space? Yeah, but if they didn't have much material, that's not the same as no material. So maybe you could have a little bit of material falling in, so little that it wouldn't get us to X-ray, but it might get us to radio. And now you need to know something about light and black holes. We talked about escape velocity radially outwards. When that velocity was equal to the speed of light, that's the event horizon in black here. But what if I wasn't going radially outwards? What if I was going sideways? Well, if I'm going sideways, maybe I could orbit around the black hole at the speed of light. Where's that? Well, it's really close to the event horizon, actually. If the event horizon is at 2 Schwarzschild radii, then this is only 1.5 times that. So really close to the black hole event horizon, light can go round in circles. If you were standing there, you could put a mirror and you could see your own head. Yeah, fun stuff. And so this is the picture that they reckoned half the world saw this picture, which is the picture of the shadow of the event horizon of a black hole. So around it, you've got this kind of glowing material that's falling towards the event horizon, but it's not very much material there at all. And you've got this sort of shadow in the middle, which is the shadow of the black hole itself. But just to kind of give it some context, the picture in the back is the optical picture of this galaxy where they were looking. So it's something like 100,000 million stars, like the sun, some a bit bigger, some a bit smaller, but it's got this kind of funky little jet in the middle. When you look in radio, you can see that actually there's something unusual in the center of this galaxy. There's material kind of squirting out that way. And right at the center of this image is where this amazing shadow of the event horizon was taken. And the size scale they're looking at here, it's like being able to read the text of a newspaper, but put the newspaper in a cafe in New York. It's like us standing in the UK and being able to read the text of a newspaper that's in New York. That's how tiny these scales are. Again, just heroic. And so you've got this accretion flow, not very much material, but it's glowing. And the glowing means it's giving off light. And the light that's close to the event horizon, if it's pointing in one direction, it can get caught in one of these circular orbits for light. And so we're able to see the light from behind the black hole come over the top and be directed towards us. But that, of course, leaves a shadow in the middle. And so this is their sort of prediction of what they're seeing. Here's that bent space-time on the bottom. Here's the black hole. And here's this fluffy little accreting flow that's a bit glowing, and the light's kind of caught and focused by the black hole. So we see this ring with a black bit in the center. It's just amazing. So I hope that I've given you at least 3 ways that we know black holes really exist. We've got these X-ray hot glowing disks that highlight all this gravitational energy released by material falling in as it approaches the event horizon. We've got this amazing image that shows us a shadow of this event horizon of a black hole. And we've got merging event horizons where you merge black holes together in gravitational waves. So Einstein's strong gravity, we can't test it any further. That's just the strongest gravity we could ever hope to observe. And it works. So where does that leave all the sci-fi stuff? Well, could we use it to build a time machine? And then I could travel back in time, but then maybe I would meet one of my grandparents. And if I accidentally killed them, if they hadn't yet had my parents, then my parents weren't born, so I wasn't born. But that would mean that I didn't invent the time machine and go back in time and inadvertently, yeah, probably not. Probably you can't use black holes as a time travel machine to the past, but you can use them as a time travel machine to the future. So black holes, strong gravity slows down time. And so if you were in very strong gravity, time for you would pass more slowly than time for a friend of yours who's free floating in space. And so you can travel to the future using strong gravitational fields, using a black hole. But I hope, for the sake of causality, that we can't go to the past. So yes, movies like Interstellar, which showed black holes slowing down time so you aged less quickly. Yeah, that's real. That's real stuff. You can travel to the future, but you can't travel to the past. And in fact, I like to demonstrate the kind of traveling to the future, because I have actually got a time machine and I can switch it on. I'm gonna switch it on, and we're gonna travel to the future. Are you ready for this?
Go ahead.
I did just switch it on, and we've all just aged by 5 seconds. We are all traveling to the future. It's called time. We can slow down the rate at which we travel, but we can't go back, according to Einstein. But hopefully not, because otherwise we get into these wild paradoxes, which wouldn't be a great plan. So yes, the Back to the Future, great movie, but probably not. So I'm going to wrap it up here so that we've got time for questions. But yeah, Einstein's general relativity, strong gravity, black holes, event horizons, we rarely see such objects. They really exist. And we could use them to do time travel to the far future, but probably not to the past. But still, it makes excellent science fiction movies. Thank you.
Chris, thank you very much. That was a very interesting thought, travelling backwards and forwards through time. If you could stop sharing your screen, and then we'll move quickly on to questions and hopefully some answers. As always, if you are joining us across the internet, put a digital hand up, please. If you're in the room, my favourite currency is £20 notes. If you throw one of those at me, we'll take questions. So I'm looking for questions from around the room. Nobody around the room. Nobody.
I see one.
Peter Lloyd. Thank you, Peter. Can we have your question, please?
Yes, hello, Chris. Lovely talk. I'm just a bit puzzled by something you talked about, and I was going to ask you about if you hadn't. You seem to imply that if you're in a spaceship close to, but just outside a at the event horizon, the orbital velocity would be equal to or greater than the speed of light. Did you say that?
So I'll go back to my slides. Oh, no, I won't. Come back. So I said the light itself, that's the orbit at the speed of light just outside the event horizon. So you would be going round at the speed of light. If you had a spaceship, you could go round at the speed of light. It's easier for photons to go around at the speed of light at just outside the event horizon.
That's what puzzles me, because normally orbital velocity is lower than the escape velocity. And if the escape velocity is the speed of light at the event horizon, then the orbital velocity should be less than the speed of light, I think. So
you're not orbiting at the event horizon. You can't orbit there. You can only orbit sort of 50% larger. So if the event horizon's at 2 GM over c squared, this is 3 times that. So 1.5 times the size scale of the event horizon, you can orbit around at the speed of light. Within that, inside that area from 1.5 to the event horizon, you can't orbit in a circle because you'd have to be going at more than the speed of light, and you can't.
Well, that's what I don't understand, because the at 1.5 times the distance of the event horizon, the escape velocity is lower than the speed of light.
It is, yes.
So if you're orbiting at the speed of light, you can't hold on and you must whiz off into space.
Well, you're going in the wrong direction. So the thing about the event horizon is you've got to be pointing directly out. So whereas here, if you're pointing in any other direction, you'll be doing funky orbits. But the event horizon is that's the escape velocity if you're pointing directly out. Don't point in any other direction or you're not going to make it.
But the International Space Station revolving around the Earth is traveling at lower speed than the escape velocity at that altitude. At least I think it is.
Well, that's because it hasn't escaped. It's
Well, exactly. So my spaceship, 1.5 times the distance from the event horizon, cannot escape if it's traveling at the speed of light. It must be able to escape, because if it goes straight out at that speed, it will escape.
I think I'd need to draw a picture. We'll save this one for when I'm actually there in person, and we'll draw pictures.
Okay, well, thank you very much. I will go and puzzle that elsewhere. Thank you.
We've got a question from in the room, Roy Johnson.
I'm just going back to a couple of things that I've read about black holes. One set says nothing can escape from a black hole. But I read somewhere about spin, that it retains information about rotation.
Yeah.
And what happens to charge? And nobody's ever explained to me, if you get an influx of, say, electrons or protons or something into a black hole, what happens to the charge? Can a black hole become electrically charged? And hence
questions. So let's do charge first. So clearly, if we put just protons down, then the black hole would start to become electrically charged. And so there'd be this sort of electrostatic pull. But there's a lot of electrons in the universe. And so if we do this in our astrophysical black holes, if we try and put charge down them, if we try and make them charged, then they'll just grab any passing electron, because these electrical forces, these electrostatic forces, are hugely stronger than gravity, actually. That's why gravity only becomes noticeable with really big things like planets and stars and galaxies. Whereas tiny little subatomic particles, they don't charge and it's noticeable. So for my astrophysical black holes, while theoretically they could have charge, anytime they grab any charge, they'll instantly have pull another one in to neutralize that charge. But if we could make black holes in a particle accelerator, so when the particle accelerators like at CERN, they're really sophisticated. They'll accelerate particles faster and faster and faster and faster and faster and faster to nearly the speed of light, and then they smack them into each other. Really sophisticated, and just see what comes out. But maybe in that smack, if it was powerful enough, maybe we could have squeezed a proton under its own event horizon, and then it would certainly have charge. But our particle accelerators are nowhere close to being powerful enough to be able to do that. So it's the sort of thing that people can explore in equations, but we can't do in, we can't really observe. But your other question was about spin, and that's something that we could kind of quite easily think of observing, because I had this material spiraling into my black hole. So it's obviously bringing spin with it. And so the material that's falling in, yes, it's increasing the mass of the black hole, but it's also making it spin. And there's only 3 things a black hole can have, according to Einstein. It can have mass, obviously, and it can have spin. That can also leave an imprint on space-time outside of the horizon. And it could have charge. That's another thing that could imprint, but won't, because any charge gets quickly neutralized. But the spin, yes, we could, and we do try and understand black hole spin. It's something you can kind of see in the gravitational wave merger signals as well. So yes, they can have spin, but not really likely to have any charge.
Okay, Roy?
Yeah.
Okay, and a question from Roy online.
Hi, Chris, can you hear me?
I can hear you.
There's a lot of talk about Hawking radiation and the evaporation of black holes. Could you just elaborate on that, please?
Yep.
I mean, what happens to them?
Right, black holes, they're black. But they don't just sit in an empty space. Even though space is a really, really good vacuum, when we go and look at space on the smallest scales, we start to get into quantum mechanics. Quantum mechanics is like the behavior of things that are very, very small. And so these subatomic particles we've talked about, you sometimes think of them as like little billiard balls, but they're a bit wavy, really. There's something about them that's more like waves than like particles, but sometimes they look a lot more like particles than waves. They're just a bit, we don't really know what is the structure of matter on these smallest scales. But quantum mechanics is the best that we have. And quantum mechanics says things that are wavy, there's a bit more kind of fuzziness about where they are and how fast they're moving. And actually, there's some sort of fuzziness about whether they're there or not. So actually, it turns out that in quantum mechanics, empty space isn't empty. You can borrow from the universe bank, and you can make a particle and an antiparticle for a small amount of time, as long as you pay it back quickly enough. So you go, hi, universe. I don't actually have any money right now, but I'll have a bit of energy, and I'll pay it back really quickly, and no one will notice. And honestly, this is our best theory. And but the thing is, if you do that close to a black hole event horizon, you've got to pay back the universe bank. But if you do it close to the black hole event horizon, there's a lot of gravitational energy. So you can grab some of the gravitational energy to pay back the universe bank, which means that your particles, or maybe photons, bits of light, have enough energy to actually exist. And they're outside the event horizon, so they can go wherever they like. Yes, really, that's what Hawking radiation is. You're borrowing from the universe bank, paying it back from the gravity of the black hole, and then you can really exist. So if you've grabbed some of the gravity of the black hole is getting lighter, it's evaporating. But the timescales for this are so long. So a star, some of these black holes that we've been talking about that come even from the collapse of massive stars, takes like 100 times, the 10 to the 100, like enormous amount of times, much, much longer than the universe has actually existed to evaporate away. But if we could make a black hole in the particle colliders, then because it's so light, it would almost instantly evaporate, which is probably a good idea. Yeah, hope that helps. But
Thank you.
Okay, Roy. Roy, okay. All right, so Greg, welcome, Greg. Can we have your question, please?
Yeah, thank you. That was a wonderful talk. I have a two-part question. First, can you just discuss the relationship between primordial black holes and dark matter? I don't know. It seems like there's some relationship there. And then I was going to ask, I read an article in New Scientist a few weeks back that like the LIGO Virgo gravitational wave detector found super black holes outside the Milky Way galaxy, but none of that size in our own galaxy. I was wondering, is there any reason for that, or is that just random? Or we look at larger black holes in the Milky Way? Yeah.
Right. Let me do the gravitational waves one first, because that's a really fun one.
Great.
So actually, all the gravitational wave sources they've detected have been outside our own galaxy. It's very, very rare that this actually happens. And so there's a lot more space outside our galaxy than in it. So that's, we've seen all our gravitational wave mergers from other galaxies. But in general, we're not very good on understanding the position, because this burst of gravitational waves kind of came from over there, and there's a lot of galaxies about. So it's really difficult without a light signal to localize it. But still, there's a lot of galaxies around, and it kind of came from over there. But in terms of the masses, the mass of the black hole is going to depend on the mass of the star that it came from and the collapsed core. And that depends on how rich an environment the star was in. If a star's in a galaxy with lots of star formation, all the metals, they kind of pollute the surface of the star, and the radiation interacts with heavy elements and pushes them away, makes a wind. And so by the time that star collapses, it's lost a lot of mass in a wind. So the black holes in our galaxy, many of them come from regions where there's been star formation, lots of metals enriching. So they've lost a lot of their mass in a wind by the time they collapse. But if you're in a small galaxy, in something like maybe the Small Magellanic Cloud, maybe if you're there, there's not that much. Stars generally don't have as much heavy elements in them, so they don't lose as much mass in a wind. So when they collapse, they're heavier. And so this is why you get some bigger black holes that we see in the merging signatures. than we've seen in our own galaxy, which is generally a kind of richer environment.
Oh, nice. Thank you for that explanation. And then, you know, is there any way
I want to do primordial black holes and dark? We don't really have a good grip on the very early universe, for the same reason that we don't have a very good grip on the singularity in a black hole. We know that when we're dealing with something very small, we want to use quantum mechanics. But when we're dealing with something that has a lot of gravity, we want to use Einstein's gravity. And so when we're dealing with something that's very small and has very strong gravity, we have to put those together. And famously, they don't get on. So we have some significant issues here, but maybe in the very early universe, gravity was so strong and fluctuations in gravity were so strong that we made mini black holes out of space-time itself. Remember, we don't have any equations. We can't do this. We can make it up as we go along. Okay, so if that happened, if gravity was like that, could those primordial black holes, could they be our source of dark matter? Could they be this extra mass in the universe? And so actually people have spent quite a lot of time and energy trying to figure that one out. And the answer is probably not. But firstly, it's black holes on a black background of space. So how would you see them? Well, actually, they got some really cunning ways to think if there was a background of these little black holes moving through space, sometime you'd look towards a whole load of stars and the images would wobble a bit and get brighter. So they looked, but they have had no clean detections. They've ruled out a lot of masses for these primordial black holes. So probably not, but we can't really do gravity on those sorts of scales in the very early universe.
Oh, thank you very much. That was a great answer. And thank you for the talk.
Thank you, Greg. Before we move on to lots, I've just got a follow-up question to Greg's. A couple of weeks ago, we had a gentleman by the name of Callum Whitman from Cambridge, who was talking about emerging from the darkness and JWST results and about early galaxies. Now, if the early galaxies are formed in a similar way to present ones, we would expect to see a black hole at the center of those galaxies.
Yeah.
Now, at 280 or 290 million years after the Big Bang, would the normal mechanism, or there must be something else happening rather than just the normal mechanism that usually makes the black hole?
So that's a kind of big open question at the moment. One of the things that JWST is starting to show is that really in the really early universe, the very first galaxies and their very first black holes, we're starting to be able to see this. We don't have great methods actually for getting really accurate black hole masses, even in the local universe, in most galaxies, let alone at these very high redshifts. But if we take our kind of standard ways of getting black hole masses and looking at these very, very young galaxies and their black holes, we're getting numbers that say, well, these black holes are a bit big, really. They're a bit bigger than we'd expect if it was this sort of normal build-up of mass into the center of a galaxy. So it's an open question at the moment. Maybe in these very young galaxies, you have a really dense star cluster, and the whole star cluster itself has merged into a bigger black hole to start the whole process, to kind of kickstart the process. Maybe actually there's so much gas that's around this newly forming galaxy that you're able to really feed the black hole fast enough to grow it faster than you might expect. Or maybe we're just wrong about some of our black hole masses. You know, it's a long way away, and we don't have really great ways of predicting maths at the moment. But it's really exciting. Give it 10 years or so, and maybe it'll sort itself out as we start to tangle with the data and start to figure out what we do and what we don't believe about it.
Okay, I have to be patient. Inside the room, lots.
I'll have the closing question.
Okay, so Mike Scollin, online. Speak to me, Michael.
I was muted. Schoolboy error. Hi. Hi, Chris. At the moment of the Big Bang, the entire mass of the universe was contained in an infinitesimally small volume. How did it manage to expand? Are we living in a black hole? Do we just need to look around to know what it's like inside a black hole?
Fabulous questions. But there is a bit of a difference. Well, firstly, remember what I said about infinities. When they come out of our equations, we've taken our equations somewhere they didn't want to go. So yeah, this is stuff we can't really do, but we can have a kind of educated guess. And so, yeah, how did it expand? That's the Big Bang, and that's the thing. We're really just making guesses. I wouldn't even call them educated guesses. But are we living in a black hole? It's not really the same thing because it's dynamic. So what you have in the Big Bang, you have, often we think of it kind of like a firework, but fireworks are exploding into pre-existing space and time. Whereas the Big Bang is not just matter and energy into existing space and time, it's matter and energy and space and time. Before the Big Bang, there was no space or time. How do you talk about before if there's no time? Yeah, I've never figured that one out either. Anyway, so space and time, and not even matter, because it's too hot for matter to exist. So there's only radiation. You have this space and time and radiation expanding together outwards. And clearly, we've said energy, radiation's the same as mass. So at some point, the universe, as it expands, it gets cooler, and you start to be able to be cool enough for photons to actually make particles. And those particles can really exist because there was a lot of energy. But you make a particle and its antiparticle. So you make an electron and a positron, and then they can meet each other and annihilate back into radiation. So actually, there's another question in here, which is, why are we made of matter, not antimatter?
We might be.
Well, whatever we're made of, we're not made of both. Because we would then annihilate in a dramatic... there was a Star Trek that did this at one point. Yeah, so somehow there's an asymmetry in matter and antimatter in the universe, and we have no idea why. That's another of these kind of, it's a kind of cosmic hint. And I'm sorry, I've forgotten what the question was.
So have I.
But it was a really good one. It was, what was it? Oh yeah, we're in a black hole, but we're not, because a black hole, the event horizon is a static thing. This is dynamic. That's where I was going. Space and time are going that away, and the whole thing is expanding. Whereas a black hole is actually a stationary thing. It's not.
Station. Yeah.
Yeah, so I would say we're not living in a black hole in the same sort of way. And we're also not living in a black hole, because in a black hole, if you try and send a photon out, it has to come back. Whereas our universe is expanding probably forever and probably accelerating as it goes.
Thank you.
Okay, I'm trying to get some sleep tonight. Don't worry about it at all. And the last question I'm going to give over to Loz.
Thanks very much. So thank you, Chris, for a wonderful talk. I just want to give you a small nod for your red dwarf joke at the beginning. It was not lost on at least me. So, or should I say Holly? So thank you very much for that. Yes, a couple of us got it.
Someone noticed. Someone noticed.
Maybe didn't acknowledge it though. Maybe we should have done. So my question is more around kind of the citizen science sort of education part of this. So as an amateur astronomer, I have lots and lots of optical equipment, and I can do some solar observation. I can do observation for stars going through supernovae and all this sort of wonderful stuff. As soon as someone mentions something, I can go do that optically. If I'm in a dark enough sky, if I've got a strong enough telescope, and if I haven't, I'll jump on my telescope and borrow one in Chile or wherever. And from a radio astronomy point of view, technology's come along to such a degree that you can get a software-defined radio that plugs in via USB to a laptop, and you can get yourself a cheap dipole. You know where this question is going, don't you? And I can do a little bit of radio astronomy and that sort of thing, or maybe I can get this data off and that's when I can do a little bit of sort of science myself. How do I go about that with X-ray and the data that comes off of the X-ray telescope? Can I do any, because obviously X-rays are blocked because otherwise we'd all be cooked and everything. Is there anything I can do, given not he who shall not be named worth of money, but let's just say I've got a pocket of money to burn. Is there something I can do? Throw up a weather balloon and do something there? Or is there something I can do with, a fibre in my pocket?
Well, one of the things that actually space astronomy led the way in was the understanding that the data we get is so precious that we share it. Not instantly. So the way it works is these telescopes in space are incredibly expensive. And so we write proposals and say, we want to look at this object. Please give us the time. And they look at all their proposals and they give the time to what they think of as the best science. And those data are private for 1 year. And after 1 year, they are archived and they are publicly available. So if you want to use data from the Hubble Space Telescope, you can go to their archive and you can download the data and you can look at it and you can work with it. If you want to use X-ray telescope data, you can go to our archives and you can look at it and you can sort of work with that. Our data is normally very interesting. In Hubble Space Telescope data, their images just look lovely. Ours normally aren't quite so pretty, but it's but yes, all the data are actually public from space missions. It's one of the requirements. Oh, apart from the Russians, but NASA, ESA, JAXA, all of their space mission data is public.
What about if I wanted to collect data myself? Is there anything I can do, being a citizen of Earth, that I can go do, given not a 7-figure sum, that I could go do to collect some X-ray sort of data, something fresh and exciting myself.
So the instrumentation itself is wildly expensive. Getting into space is getting cheaper, but it's still wildly expensive. But there are things like the AAS, the American Association of Variable Star Observers. They do observations of variable stars, and they're with optical telescopes, and their data gets used. And that they actually also have act as like a link between the amateur astronomers and the professional astronomers. And sometimes they get together and write proposals for data, including data from some of these telescopes in space. So those sorts of observing societies, they do give a kind of way in to work with professional astronomers and actually apply for time on some wild X-ray satellite. So yes, if you're interested, the American Association of Variable Star Observers, I think, is the way to go.
Okay, Ross.
Thank you, Holly.
So just before you go, you had a slide showing a sounding rocket when talking about a Nobel Prize in the 1960s. We have a Skylark sounding rockets up a stage.
So I'm sorry, you have sounding rockets?
We have a sounding rocket, a Skylark up a stage.
Ah, yes.
And I believe that we have got some X-ray detection equipment that actually flew into space.
Yes.
In our
March 1970.
yeah. Royce free my ear. It flew in March 1970. So if you want some pictures of some very old equipment, I'm sure we can get some for you.
So my boss in Leicester was Ken Pounds, and he did a lot of some of these early flights of sounding rockets and the kind of early space stuff. And yes, so you see some of these. In fact, I have. We had a conference there, and they gave us all a little rocket for 50 years of space astronomy at the University of Leicester. But I thought that was really rather sweet, and it joins my collection. This is my NASA patch from the mission that we flew on the shuttle.
Now you just went just jealous, Rich. This is spotlit. So that just leaves me to thank you very much. Thank you for a wonderful talk tonight, and thank you for answering all the questions. Can everybody join me in giving a big thanks, for instance, to Astronomical Society? Thank you to Professor Chris Done. Thank you very much.
Thank you.